Welcome to Late Night History. Settle in, let the lights go low, and let the room go soft around you, because tonight there is nothing you need to do, nowhere you need to be, and no part of this story you have to hold on to if your eyes grow heavy. It will keep. It has kept for a very long time already. Tonight we are going to go down into the earth, slowly. The way you might descend a long staircase in an old house by candlelight, one worn step at a time, and we are going to look for something that almost nobody has ever seen. Here is where we begin. Roughly 38% of the entire Earth, by volume, is made of a single mineral. Not 38% of the crust, not 38% of the rocks you could pick up on a walk. 38% of the whole planet, the entire ball of it from the thin skin we live on, all the way down toward the burning heart at its center. More than a third of everything beneath your feet is one kind of crystal, one repeating arrangement of atoms, more of it than any other mineral in the world. And yet, until the year 2014, not one human being had ever laid eyes on a natural grain of it. Not a geologist, not a miner, not a museum curator standing over a tray of specimens. No one. Sit with that for a moment, because it is a strange and quiet kind of wonder, the sort that is easy to miss in the rush of a waking day but settles gently into the mind at night. The most common rock inside our planet, the stuff that most of the Earth is literally made of, was, for the whole of human history, invisible. We had never held it. We had never touched it. We did not even have a proper name for it, and the reason for that, the reason this most ordinary of substances managed to stay hidden while we mapped the ocean floors and photographed distant galaxies and split the atom, is one of the loveliest small mysteries in all of science. That is the story we are going to unfold tonight, slowly, with no hurry at all. The mineral is called bridgmanite. It is a soft word, isn't it, bridgmanite, with a gentle fall at the end of it. Say it once to yourself and let it go. We will come back to where that name comes from later, and to the man it honors, a physicist who spent his life squeezing matter under pressures almost beyond imagining. But for now, just hold the name. Bridgmanite, the commonest rock on Earth, and one of the last of the great abundant minerals to be given a name at all. And here is the part that turns this from a simple fact into a real story. The way we finally came to hold it, or as close to holding it as anyone has ever come, was not by drilling down into the earth. We have never drilled anywhere near deep enough, and as you will see tonight, even if we could, it would do us no good, because this particular mineral will not survive the trip to the surface. No, the way we finally captured a natural grain of Earth's most abundant mineral was that a piece of it fell out of the sky. In 1879, in the state of Queensland, in the northeast of Australia, a meteorite came down. People saw it fall. It was what astronomers call a witnessed shower, meaning the stone broke apart in the sky and scattered its fragments across the ground while human eyes watched it happen more than 140 years ago now. The stone is known today as the Tenem meteorite, named for the place where its pieces were gathered. It is an ordinary chondrite, which is the most common sort of stony meteorite there is, the plain grey bread and butter of the solar system, classified by scientists with the modest label L6. There is nothing about the outside of it that would stop you in the street. If you held a fragment in your palm, you would think it a dull, heavy, unremarkable rock, the kind of thing a child might pocket on a beach and forget. But inside that unremarkable stone, sealed away in thin dark seams running through it, was a treasure that no laboratory on Earth had ever managed to obtain. And in the year 2014, more than a century after it fell, two scientists finally read what was written there. Their names were Oliver Chawner of the University of Nevada in Las Vegas and Chi Ma of the California Institute of Technology, working with a small group of colleagues. On the 28th of November, 2014, they published their finding in the journal Science, and the title of their paper said plainly what they had done. They had discovered bridgmanite, the most abundant mineral in Earth, in a shocked meteorite. After decades of knowing it must exist, after decades of making it in the laboratory but never possessing a natural piece, a stone that fell in Queensland in the year 1879 had finally given it up. We will walk through every step of how they did it, and why it was so hard, and why a meteorite of all things was the answer. But there is no rush. That is the whole point of tonight. So before we go any deeper, let me ask you something, the way I like to at the start of these slow journeys. Wherever you are listening from tonight, whatever corner of the world has gone dark around you, I would like to know. Leave a comment and tell me where you are, what city, what country, what quiet room. It is a small thing, but there is something warming about knowing that this same old story is being heard in so many different places at once, under so many different night skies. And if you are new here, if you have only just found this quiet corner, you are welcome to stay. Settle in, and if you would like more slow stories of this kind to drift off to, you might subscribe, so the next one finds its way to you. There, that is the only asking I will do for a good while. Now let us go back down into the earth. So, what is this mineral, this bridgmanite, that fills more than a third of the planet, and yet stayed hidden for all of time until a decade or so ago? Let us take it gently, one piece at a time, and if any of the harder words slide past you as you drift, do not worry, because I will always tell you what they mean in plain language in the same breath. Bridgmanite is a silicate. That word simply means it is built mostly from silicon and oxygen, the two most common ingredients in the rocks of the Earth. The same pairing that makes up ordinary sand and quartz and the greater part of nearly every stone you have ever seen. To that silicon and oxygen, bridgmanite adds magnesium, a light, common metal, the same element that makes the bright flare in an old-fashioned flashbulb, and a smaller amount of iron, the heavy metal that gives rust and blood their colour. Chemists write its recipe as magnesium and iron together with silicon and oxygen in a tidy formula, but you do not need the letters tonight. You only need the idea. Magnesium, iron, silicon, oxygen, four of the most ordinary elements in the Earth, arranged in one particular, very tightly packed way. And that arrangement, the way the atoms are stacked together, is the real secret of what bridgmanite is. It has what scientists call a perovskite structure. Now that is a word worth slowing down for, because it is easy to mishear it as a description of what the mineral is made of, when it is really a description of the shape the atoms make, the architecture of the thing. Think of it this way. You could build two very different houses out of the very same bricks, one a low cottage and one a tall tower. And the bricks would be identical, while the shape would be entirely different. Perovskite is a shape, a floor plan for atoms, not a particular set of bricks. Scientists sometimes write that plan as a simple pattern, one kind of atom, then another, then three of a third, repeating over and over in every direction, a framework as regular and as patient as tiled floors running away down an endless corridor. The shape gets its name from an actual mineral, a stone called perovskite in the ordinary sense, which is made of calcium and titanium and oxygen, and which was found and named long before anyone dreamed of what waited in the deep earth. When scientists realized that the deep mineral arranged its own atoms in that very same floor plan, they borrowed the name for the shape. So bridgmanite is a silicate perovskite, which is only a way of saying it is made of silicon and magnesium and iron and oxygen, arranged in that particular ancient architecture first recognized in a humble calcium titanium stone. And in bridgmanite, that architecture is very slightly bent, a little distorted, the corridors not perfectly square, but leaning just so. The way the walls of a very old house settle out of true over the centuries. That gentle distortion is part of what makes it stable so far down, and part of what makes it fall apart so easily when it comes back up. But we will get to that. For decades, before it had a proper name, this is exactly what scientists called it. Not bridgmanite. They called it silicate perovskite, or magnesium-iron silicate perovskite, a careful, clumsy, descriptive mouthful, the way you might refer for years to a neighbour you have never actually met as simply the person in the house at the end of the lane. They knew what it was. They knew what it was made of and what shape it took. They simply were not allowed to give it a true name. For a reason that is going to become one of the small aching ironies of this whole story, and which I will come to a little later once we have gone deeper. Because now we should ask the question that really matters. Where does all this bridgmanite live? Where is this hidden ocean of the commonest rock on Earth? This 38% of the whole planet that no one had ever seen? To answer that, we have to leave the surface behind entirely and go down, far down, past everything familiar, into a layer of the earth called the lower mantle. Let me set the scene for you, slowly, so you can feel the descent. Imagine you could sink straight down through the ground beneath you, gently, without heat or harm. Just drifting downward through the earth like a feather falling through still water. First you would pass through the crust, the thin outer skin, where all of life happens, where the cities and the forests and the oceans and every human being who has ever lived have made their whole home. The crust is astonishingly thin, thinner in proportion than the skin on an apple. Only a few tens of kilometers deep beneath the continents and thinner still beneath the seas. You would fall through it in no time at all. Below that you would enter the mantle, the vast, hot, slowly churning layer that makes up the great bulk of the Earth, a thick shell of rock wrapped around the planet's metal core. And you would keep falling, down past the upper mantle, down through a strange in-between zone that scientists call the transition zone, where the rock changes its character with the growing pressure. And then, at a depth of about 660 kilometers below the surface, you would cross a very particular boundary, a line where everything changes, and you would enter the lower mantle at last. The lower mantle runs from that boundary at around 660 kilometers down, all the way down to roughly 2,890 kilometers, where it finally meets the outer edge of the Earth's core. That is an enormous stretch, more than 2,000 kilometers of rock, far deeper than any drill has ever reached, far deeper than any mine, deeper than the deepest ocean trench many times over. And here is the thing that ought to make you pause in the dark. That single layer, the lower mantle alone, is about 55% of the entire volume of the Earth. More than half of our whole planet is this one deep layer, this one dark region that no eye will ever see, that no light has ever touched, where the pressure is crushing and the heat is enormous, and the rock flows as slowly as the hour hand of a clock. And the lower mantle is made, in the great majority, of bridgmanite. Somewhere between 70 and 80% of all that rock, all that 55% of the earth, is our shy hidden mineral. Now you can see how the numbers add up to that astonishing figure. If the lower mantle is more than half the planet, and bridgmanite is most of the lower mantle, then bridgmanite must be a huge slice of the whole, roughly 38% of everything. The single most abundant mineral inside the earth, and very likely the most abundant solid mineral in all the rocky planets. The same crystal probably filling the deep interiors of Mars and Venus and Mercury as well, a substance so common across the inner solar system that it may be, in the most literal sense, what worlds are made of. The rest of the lower mantle, the part that is not bridgmanite, is mostly a couple of other deep minerals keeping it company down there in the dark. There is a mineral scientists call ferropericlase, which is a simpler thing than bridgmanite, made of magnesium and iron together with oxygen, without the silicon. Ferro for the iron, periclase for the magnesium-oxygen part. It is bridgmanite's constant partner in the depths, the two of them woven together through that whole vast layer. And there is a third, less abundant deep mineral, a calcium silicate that also takes on that same perovskite architecture, which was itself only given a proper name in recent years, and which is called diamond-anvil. We will meet diamond-anvil again later tonight, because its story, the story of how it too was finally named, rhymes with the story of bridgmanite in a way that is worth hearing. But for now it is enough to know that down there in the lower mantle, bridgmanite is the great sea, and ferropericlase and diamond-anvil are the lesser things that swim in it. So let us gather what we have, quietly, the way you might lay a few smooth stones side by side before sleep. More than a third of the earth is one mineral. It fills the lower mantle, a layer that is itself more than half the planet, a region deeper than any drill has reached, hotter than any furnace we build, under pressures that would crush anything from the surface world in an instant. And that mineral, that overwhelming majority of the deep earth, that stuff of which most of the planet is made, had never once been seen by human eyes, until a stone that fell from the sky in 1879 finally gave up a grain of it in the year 2014. This is the enigma we are going to sit with tonight, and I want to state it plainly now, so it can settle into you as you drift, because everything that follows will be a slow circling around this one strange fact. Most of the earth is made of a mineral no eye had ever seen. Not because it is rare, it is the opposite of rare. It is the commonest rock in the world. Not because it is hidden in some difficult tucked-away place, some single vein in some far country. It is everywhere beneath us, all the time, all at once, an ocean of it larger than every ocean of water, combined many times over, filling the greater part of the ground under every city and every sea. And still, for all of human history, no one had held it. No one had seen it. It managed to be, at the same moment, the most abundant substance on earth and one of the very last to be caught. How can that be? How can something be everywhere and yet unseeable? How can a thing you are, in a sense, always standing on top of, always surrounded by, a thing that makes up more of your own planet than anything else, be something you can never dig up and never hold? That is the question. And the answer, when we come to it, is one of the most elegant and quietly astonishing things in all the study of the earth. Because the reason bridgmanite is invisible is not that it hides from us. It is that it cannot survive the journey up to where we could ever meet it. It unmakes itself on the way. It is a mineral that only exists in the deep under the great weight of the world pressing down on it. And the moment that weight is eased, the moment it begins to rise toward the light, it quietly comes apart and becomes something else. So that by the time any piece of the deep mantle reaches the surface, whatever bridgmanite it once held is long gone, transformed into humbler minerals before it ever sees the sky. Slow geology, the ordinary rising of rock over millions of years, can never bring us a sample. That is the heart of it, and that is why, out of everything in the world, it took a meteorite, a violent thing, a fast and frozen thing, to trap a grain of it for us at last. We will come to exactly how that violence works its magic, how a collision in space more than a century ago managed to catch and hold what all the slow patience of the earth never could. But that is for a little further down the staircase. For now, let yourself rest for a moment on the plain wonder of it. Beneath you, right now, wherever you are, wherever this quiet voice reaches you, there is rock. And below that rock, more rock, and below that more, warmer and denser and heavier, mile after mile of it, deeper than thought. And most of it, the overwhelming bulk of the ground that holds you up, the great dark body of the world, is made of a mineral that until only about 10 years ago no living person had ever seen with their own eyes. You are lying on top of an ocean of the unknown. You have been your whole life. Everyone who has ever lived has slept, as you may be beginning to now, on a hidden layer of a crystal they never once glimpsed. And the strangest part, the part we will turn to as the night deepens, is that even though we had never seen it, we came to know it astonishingly well. Long before that meteorite gave up its grain, long before anyone could point to a single natural piece of it, we knew how dense bridgmanite was. We knew how fast sound would travel through it. We knew, in fine detail, the temperatures and pressures at which it could exist, and the exact depth at which it would be born. We had, in a sense, read the whole hidden character of this mineral we had never touched. The way you might come to know a person very well through their letters alone, through their handwriting and their turns of phrase, long before you ever meet them face to face. We knew bridgmanite as a fingerprint pressed against the far side of a locked door. And we came to know it not by digging for it. We came to know it by listening to the deep ringing of the earth itself, to the way the great shudders of distant earthquakes travel down through the planet and back up again, slowing here, speeding there, bending around the hidden layers like light bending through water, and in that slowing and speeding, telling us, for anyone patient enough to read it, exactly what the deep rock must be. We listened to the earth ring, and the ringing spelled out the presence of a mineral we would not hold for another lifetime. But I am getting ahead of myself, and there is no need to hurry. We have laid the first stones. We know now what bridgmanite is, this silicate crystal of magnesium and iron and silicon and oxygen, stacked in the gently distorted perovskite architecture first named for a humble calcium-titanium stone. We know where it lives, in the lower mantle, that vast dark layer running from 660 kilometers down to nearly 2,900, more than half the planet, 70 to 80% of it made of our mineral. with ferropericlase and davamoite keeping it company in the depths. And we know the enigma we have come here to sit with, the beautiful contradiction at the centre of it all. The commonest rock in the world, and no eye had ever seen it. The most abundant mineral inside the earth, and it destroys itself before it can ever reach the light. Rest there a while. Let the numbers grow soft and dreamlike. 38% of the earth. 660 kilometers down. A stone that fell in 1879. A grain smaller than you could ever imagine, waiting in the dark of a meteorite for more than a century, for the day we would finally have the patience and the tools to read it. Let all of it drift, and do not try to hold on to any of it. It will keep. It has kept for the whole age of the earth, and it will keep until morning. And as you begin to sink a little deeper into the quiet, let me tell you where we are going next, so that some soft part of your mind can follow along, even as the rest of you lets go. We are going to ask the real question, the one at the centre of the whole mystery. Not just that bridgmanite hides, but how it hides. Why a mineral that fills most of the planet cannot simply be dug up. Why the slow rising of the Earth's rock, the very same process that brings us diamonds and lava and all the deep treasures we do hold in our hands, can never, not once in all the ages of the world, bring us a single surviving grain of the commonest mineral of all. Because there is a reason. A precise, physical, almost gentle reason, having to do with pressure and with the way that certain crystals can only keep their shape while the whole weight of the world is pressing down upon them. Ease that weight, and they change. They loosen. They rearrange themselves into other simpler things, the way a tightly clenched hand relaxes and opens when the effort is released. Bridgmanite is a clenched hand, holding its shape only under the crushing grip of the deep earth. And on the long, slow journey up toward the surface, as the grip eases mile by mile, the hand opens, the crystal lets go of its perovskite architecture, and the mineral quietly unmakes itself into ordinary rock long before it ever nears the daylight. That is why the slow way can never work. And that is why, in the end, it took the fast way, the violent way, the way that comes not from below but from above, out of the cold dark of space, to catch a piece of it and freeze it in an instant before it could ever change. A collision, a shock. A few seconds of pressure and heat as fierce as the deep mantle itself, and then a sudden, merciful cooling. Quick enough to trap the crystal exactly as it was, to lock the clenched hand shut forever, so that 135 years later, on the far side of the world, 2 patient scientists could finally open the stone and read what was written inside. We will walk that path together, slowly, on the next stretch of the staircase. How the mineral unmakes itself, and why. How the shock of a cosmic collision does what all the gentle patience of the earth never could. And how, for 40 long years, we could build this mineral with our own hands in the laboratory, could make it whenever we wished, and yet were not allowed to give it a name. Because of a single quiet rule that says a thing is not truly named until nature herself has handed us a piece of it. There is an ache in that, and a beauty, and we will sit with it when we come to it. But not yet. For now, there is only the dark, and the deep, and the soft weight of a whole hidden world beneath you. Breathe out. Let the day go. The ground beneath you is older than anything you will ever have to worry about, and it is made, most of it, of a quiet crystal that waited patiently in the deep for the whole of human history before it let itself be known. There is no hurry in any of it. There never was. And so we begin to descend more slowly, the way the earth itself descends, in layers, each one heavier than the one above, each one defined by the thing it is made of and the pressure under which it lives. The thing bridgmanite most wants to do is exist. That sounds too simple to be interesting, but stay with it. Every mineral has a range of conditions in which its particular arrangement of atoms is the lowest energy option. The arrangement the atoms prefer, the way they would choose to sit if they were allowed to choose. For bridgmanite, that preferred range is deep, very deep. Below approximately 660 kilometers from the surface of the Earth, the pressure climbs above roughly 23 gigapascals, 23 billion pascals, if that number means anything to you. Or to put it in terms that might sit more easily in the mind as you lie quietly in the dark, more than 220,000 times the pressure of the air resting on your chest right now, which is itself already pressing down on you with the whole weight of the atmosphere, and you do not feel it, because your body has always lived inside it and knows no other reference. 220,000 of those. That is where bridgmanite begins. That is the floor of its comfort, the lower edge of the door it needs in order to be what it is. Below that boundary, going down through the great dark of the lower mantle to the very edge of the liquid iron core at about 2,890 kilometers, bridgmanite is stable. It is at home. It sits in its distorted orthorhombic arrangement with the quiet confidence of something that has always known where it belongs. But bring it up. Begin the long, slow journey toward daylight. And the world changes. This is the thing that kept bridgmanite hidden from human eyes for the entire length of human history. Not secrecy, not depth alone, though the depth is formidable. What kept it hidden was this: the moment the pressure around it begins to fall, the moment the rock that contains it begins to rise, even fractionally, even by the geological equivalent of a whisper, bridgmanite begins to change. It does not shatter, it does not dissolve, it rearranges. The atoms find new configurations that are more stable at the new, lower pressure, and they move into those configurations with the slow, inevitable patience of a crystal following its own nature. The magnesium and iron and silicon and oxygen that were locked into the perovskite architecture, the distorted cage of ABX3, the same repeating geometry as calcium titanate, the same basic lattice that organizes so much of the deep earth, those atoms do not cease to exist. They simply reorganize into something else, into minerals that are stable at shallower pressures, into enstatite, into pyroxene, into the ordinary rock-forming silicates that populate the upper mantle and the crust and the volcanic landscapes we have always been able to reach and study and name. Bridgmanite, as it rises, becomes something else. Not dramatically. Not with any violence that would leave a trace you could point to later and say, here, this is where the transformation happened. It simply and silently unmakes itself. The geologists have a phrase for this kind of behavior, and it is exactly as calm and precise as the process it describes. They call it decompression instability. The mineral is unstable under decompression, unstable when the pressure falls away. And the consequence of that instability, played out over the whole of geological time, is that no volcano has ever delivered a piece of bridgmanite to the surface. When mantle rock rises in a plume, when magma forces its way upward through the crust, when xenoliths, those fragments of the deep mantle that get carried up in kimberlite pipes like passengers on an unlikely train, when any of this slow and ordinary volcanic transport happens, the bridgmanite that was there, deep down, has already changed before it arrives. The journey takes long enough, and the decompression is gradual enough, that the transformation is complete by the time the rock sees anything approaching daylight. What reaches the surface is enstatite, pyroxene, the minerals of the upper world. The bridgmanite is gone, not physically removed, but chemically transfigured. The way a block of ice left on a warm stone eventually becomes a pool of water, and then a patch of damp, and then nothing at all that you could point to and call ice. Quick reminder, after years of lying awake with a racing mind, deep sleep finally became possible. Now learning comes easier, energy is real, and the mind stays sharp. Sleeping like a baby changed everything. If you want the exact system that made this possible, check the link in the pinned comments. This is why, for the entirety of recorded human history and for all the millennia before it, no one had ever seen bridgmanite. Not because it was rare, not because it existed only in some exotic corner of the earth that humans had not yet visited, but because the Earth itself, in its slow and patient geological processes, erased every specimen on the way up. The planet makes this mineral constantly, in enormous quantities, across a layer that accounts for the majority of the planet's volume. And the planet destroys every piece of it that tries to reach the surface. Not out of malice, not out of any intention at all, simply because of physics, because of the thermodynamics of crystal stability, because below 660 kilometers the atoms want to be in one arrangement, and above that boundary they want to be in another, and they will, given enough time, always find their way to the arrangement they prefer. Slow geology erases it. That is the sentence that lives at the heart of this whole story, and it is worth holding for a moment before moving on, because it reshapes the question of how the mineral was finally found. If slow geology erases it, then the only possible path to a preserved specimen is something fast. Something so fast that the transformation cannot keep up. Something that creates the pressure and then removes it not over millions of years, not over thousands, not even over hours or minutes, but over seconds. A geological event that runs faster than a crystal can change. There is only one obvious candidate for that kind of speed, and it does not come from inside the Earth at all. It comes from space. When a large object, an asteroid, a rocky body, something solid and dense and moving at several kilometers per second, strikes another body in the dark of the solar system, the energy of that collision converts almost instantaneously into pressure and heat. The shock wave that propagates through the rock at the moment of impact is not like the slow squeeze of burial, not like the gradual accumulation of the weight of kilometers of stone above. It is a pulse. A hammer blow transmitted through solid rock at speeds that dwarf anything a geological process can manage. For a brief window, lasting not millions of years, not thousands, not even hours, but seconds, a handful of seconds at the outside. The pressure inside the rock reaches values that rival the lower mantle itself. 23 gigapascals. 25. The rock at that moment is experiencing conditions it would otherwise only encounter at a depth of 600 kilometers or more. And in those seconds, minerals that can only exist at those pressures have the opportunity to form. And then the shock passes, the pressure collapses. The rock, which has not moved from where it was, which is still sitting in the asteroid belt or wherever the collision occurred, cools rapidly in the vacuum of space, far more rapidly than any piece of mantle rock rising slowly toward a planetary surface. The quench, the word geologists use for that sudden drop in temperature and pressure that freezes a crystal in its high-pressure form before it can transform, the quench happens in the span of seconds, and the crystal, caught mid-formation or fully formed in that brief window of extreme conditions, finds itself locked into a configuration it would normally only maintain deep inside a planet. It has no time to rearrange. The pressure is gone before the atoms can respond, and so the structure persists, sealed inside the matrix of the surrounding rock, a tiny prisoner of timing. This is exactly what happened inside the Tenem meteorite. The Tenem stone fell in Queensland, Australia, in 1879. It fell as a shower, not one stone but many, distributed across the landscape in the way that meteorites often arrive when the parent body is large enough and the fragmentation occurs high enough in the atmosphere that the pieces spread before landing. It is classified as an L6 ordinary chondrite. The L tells you about its iron content, placing it in the low iron group of ordinary chondrites. The 6 is the petrologic type, describing how thoroughly the meteorite has been thermally and chemically processed since it formed. A 6 is well equilibrated, its minerals thoroughly recrystallized, its original primitive textures largely overwritten by the long, slow cooking that happens when a body sits in the solar system and gradually accumulates heat from radioactive decay. The ordinary chondrite designation tells you it is not exotic, not a visitor from the crust of a differentiated asteroid or a piece of the Moon or Mars. It is ordinary rock, the kind of rock that makes up most of the rocky debris of the inner solar system, descended from the undifferentiated material of the early nebula. But Tenem is also something else. It bears the mark of a collision so violent that it has its own shock grade, S6. The S stands for shock, and the number indicates the degree to which the rock has been metamorphosed by impact. S6 is the highest shock grade short of total melting, the grade at which the rock has been subjected to such extreme pressure that it shows pervasive evidence of transformation, planar deformation features in its crystals, high-pressure polymorphs of ordinary minerals, and most visibly, when you look at a thin section of the stone under a microscope, the dark, sinuous features called shock veins. Shock veins are exactly what they sound like, though the analogy to veins in a body is imperfect. They are thin seams, dark and glassy-looking, that cut through the lighter-coloured matrix of the meteorite like threads of shadow woven through ordinary stone. When the impact shock wave passed through the rock, the local stress concentrations at grain boundaries and other heterogeneities caused small pockets and thin channels of material to melt instantaneously. The pressure and the frictional heating were sufficient to briefly liquefy the rock along those narrow pathways, and inside those pathways. For the few seconds during which the shock pulse was at its maximum and the pressure was highest, conditions resembling the lower mantle existed. Approximately 23 to 25 gigapascals of pressure. Temperatures on the order of 2,000 degrees Celsius. A violent, transient, miniature facsimile of the world 600 kilometers beneath the surface of the Earth. Produced not by depth and burial, but by the kinetic energy of a collision travelling at several kilometers per second. And then it ended. The shockwave passed. The molten material in the veins quenched, cooled so rapidly that the high-pressure minerals forming inside it were frozen in place before they could transform. The vein solidified, sealing the new crystals inside like insects preserved in amber or like a letter sealed in an envelope and never opened. The asteroid, or the fragments of it, drifted through space. Eventually, after some journey that took perhaps hundreds of millions of years, or less, the details of which the stone does not fully disclose, Some of those fragments intersected the orbit of the Earth and fell, one Queensland morning in 1879, into the red dust of the Australian interior. There, inside the dark threads of the shock veins, were grains of bridgmanite, tiny ones. The grains are submicron to a few micrometers across. A micrometer is a millionth of a meter, and a human red blood cell is roughly 7 to 8 micrometers in diameter. Which means some of these bridgmanite grains are smaller than a red blood cell, and the largest are barely the size of one. You could not pick one up. You could not place one on a glass slide and look at it with an ordinary microscope and know what you were looking at. You could not, in any meaningful physical sense, hold one of these grains. The word hold in the title of this story, How We First Held Earth's Most Common Rock, is not literal in the way you might hold a stone from a beach or a crystal from a mineral shop. It is something more like how you hold the memory of a conversation, or how you hold the image of a face you have not seen in years. You hold it in the sense of having it, of having grasped it, of being able to examine it and know what it is, even if it never rests in the palm of your hand. Holding a grain of bridgmanite meant reading it. And reading it, as we will come to see, was itself an adventure that took decades longer than finding it. But before we come to the reading, it is worth sitting for a moment with the strangeness of the 40 years that preceded it. The year is 1974, or thereabouts, and a physicist named Lin-gun Liu is working at the Australian National University. The diamond-anvil cell, a device in which two gem-quality diamonds are pressed face-to-face with a tiny sample squeezed between their polished tips, had by that time become a capable instrument for generating very high pressures in the laboratory. Percy Bridgman, the Harvard physicist after whom the mineral would eventually be named, had spent much of the first half of the 20th century building and refining the pressure apparatus that made all of this possible. The high-pressure pistons, the Bridgman anvils, the seals and gaskets that prevented a sample from simply squirting out from between the plates when you tried to compress it to extreme pressures. His work, which earned him the Nobel Prize in Physics in 1946, laid the foundation for an entirely new branch of materials science, the branch that studies what matter does when you squeeze it hard enough that its very atomic structure begins to change. The diamond-anvil cell is a descendant of Bridgman's anvils, miniaturized and refined. The gem diamonds serving as anvil tips because diamond is the hardest known material and will not deform under pressures that would crush any other substance you might choose. Liu placed magnesium silicate, MgCO3, the pure magnesium end of what would become bridgmanite's composition range, between the diamond tips and squeezed. He squeezed past the pressures of the upper mantle, past the transition zone, past the 660-kilometer boundary, and the material transformed. Under pressures above approximately 23 gigapascals, the MgCO3 adopted a new crystal structure, the perovskite architecture, the distorted orthorhombic arrangement with the space group designation PBNM, the same fundamental geometry that the mineral calcium titanate displays and that gives perovskite its name, after the Russian mineralogist Lev Perovsky, for whom the original calcium titanate mineral was named in the 19th century. In that distorted cage of atoms, 8 coordinated magnesium ions and 6 coordinated silicon ions interlocked with oxygen in a repeating pattern, a structure both rigid and slightly, elegantly bent, like a cathedral whose arches are fractionally, not quite symmetrical, and all the more stable for it. Liu had made it. He had, in the laboratory, produced Earth's most abundant mineral. He could do it whenever he wished. He could instruct a graduate student to do it. The recipe was known, and the equipment to follow it was available in high-pressure physics laboratories around the world. And yet this mineral had no name. It was called, in the scientific literature, silicate perovskite, or MgCO3 perovskite, or sometimes lower-mantle perovskite, or high-pressure MgCO3, or various other descriptive phrases that circled around the thing without landing on it. These are not names in the mineralogical sense. They are descriptions, placeholders, committee compromises. The way you might refer to a child you know is coming, but has not yet been born. The baby, the little one, the one who is almost here. The International Mineralogical Association, the body that governs the naming of minerals, that decides what is a valid species and what is merely a variety or a polymorph, has a rule that is simple and very old and, in this case, produced a silence lasting 4 decades. A mineral cannot be formally named without a natural terrestrial holotype specimen. Not a synthetic sample, however carefully made, not a theoretical model, however accurate, not a crystal grown in a high-pressure cell in a physics laboratory, even if that crystal is chemically and structurally identical in every measurable way to the mineral you want to name. The name requires a piece of nature, a specific piece, with a specific location and a specific museum catalogue number, a piece that other scientists can examine and verify and compare their own samples against. The holotype is the anchor of the name, the physical thing that the name points to, and without the holotype there can be no name. For approximately 40 years, from Lin-gun Liu's synthesis in the mid-1970s until the autumn of 2014, humanity possessed the knowledge and the equipment to make Earth's most common mineral. And the mineral sat unnamed because nature had not yet consented to hand us a piece of it. We had built it. We had characterized it. We had used our knowledge of its density and elastic properties to map the entire lower mantle. We had woven it as a concept through the architecture of planetary science. And we could not name it, because a crystal made in a laboratory, however real, however identical, does not count. The rule says so. The rule is not arbitrary. It exists because a named mineral is an anchor in the physical record, something future scientists can return to and verify and build upon, and a synthetic sample does not provide that kind of anchor the way a natural specimen does. The rule is good and defensible, and it produced, in this case, 4 decades of a mineral existing in plain scientific sight while remaining technically unnamed. There is something in that situation that feels, in the quiet of the night, like a parable about the difference between knowing and having. We knew this mineral, we knew its formula, its structure, its density, its sound velocity, its stability field, its role in the architecture of the planet. We knew it, in the sense that we could reproduce it and measure it and use it as the backbone of our model of the deep earth. But we did not have it. We did not have a piece that nature had made herself in her own way by her own processes, without our help. And until we had that piece, the name could not be given. The mineral could not be properly born into the catalogue of the world's substances. What would it take? A piece of bridgmanite that had formed not in a laboratory but in nature. A piece that was stable enough to survive until someone could examine it. A piece that had somehow avoided the decompression instability that erases every specimen geology tries to bring to the surface. A piece, in other words, exactly like the one sitting quietly inside a museum specimen of the Tenem meteorite, waiting in a shock vein, in grains smaller than a red blood cell, since a morning in 1879 in Queensland, Australia, for the right question to be asked and the right tools to be turned upon it. That it took until 2014 for those tools to arrive is not a failure of imagination or of effort. It is, as we will come to understand, the story of a problem that required both the right material, a meteorite shocked hard enough and preserved carefully enough, and the right instrument. And for a long time, the instrument that seemed most suited to the task was exactly the wrong one. But that is the path into the next part of the story, and we will walk it at the same unhurried pace we have kept throughout, because there is no reason to rush. The mineral waited in the stone for over a century. The stone is patient still, and the night around you is long and soft and full of room for one more slow, careful step into the dark. For now, close your eyes if you have not already. Feel the weight of the bed beneath you, the weight of the air, 220,000 times lighter than the pressure under which bridgmanite lives, and yet somehow enough, in this moment, to hold you exactly where you are. Somewhere below your city, below the foundations of every building, below the deep roots of mountains, below the ancient rock of the crust and the upper mantle. The lower mantle begins its long, unlit descent, and most of what is down there is bridgmanite, sitting in its distorted cage of atoms at pressures no human instrument in the field has ever directly measured. By temperatures that dwarf the hottest industrial furnace, making up most of the world you live on, and extending in every direction around the liquid iron heart at the center of everything. It waited 4 billion years. It waited all of human history. It waited for the right stone to fall in the right place, and for the right tools to be invented, and for 2 patient scientists to ask the right question of a grain smaller than a cell in your blood. And in 2014, it finally let itself be known. We are almost at that moment, almost at the part of the story where the instruments arrive and the name is given and the 4-decade silence is ended. But first there is the question of why earlier attempts failed, and how, in failing, they opened the way for the technique that finally succeeded. And there is the question of how we knew so much about this mineral before we ever had a piece of it, how we mapped a hidden world, not with drills or samples, but with sound, with the murmur of earthquakes travelling through rock at depths no human or human machine has ever reached. How we came to know bridgmanite by listening before we came to know it by looking. That is the part of the story that sits at the quiet heart of the whole thing, and we will come to it in the next slow turning of the night. And yet the reason it hides is so simple, so inevitable, that once you understand it, you feel almost foolish for not having expected it. Bridgmanite does not hide because it is rare. It does not hide because it is fragile in some ordinary sense of the word. It hides because the conditions that make it possible, the enormous, crushing weight of 660 kilometers of rock pressing down from above, are the very conditions that the surface of the earth will never, under any ordinary circumstance, remove that pressure, even slowly, even gently, and bridgmanite begins to change. It reorganizes. The tight, distorted cage of atoms that the perovskite structure requires at those depths loosens and rearranges itself into something the surface world will accept. Into pyroxene, into enstatite, into the ordinary mineral phases that you can find in any geology collection, on any shelf, in any university department, with a display case and a handwritten label. The stone comes back, but it comes back as something else. It has unmade itself on the way up. This is what happens when a piece of the lower mantle rises toward the surface, as it does in the long, slow churning of mantle convection, as it does when a volcanic plume carries deep material upward, as it does when a fragment of ancient rock is dragged to shallower levels over millions of years. The bridgmanite does not survive the journey. By the time the rock approaches anything like the pressures found in the upper mantle, somewhere well above that 660-kilometer line, the transformation has already begun. And it continues on the way up through the crust, through the volcanic conduit, through the eruption itself. And whatever piece of the deep lower mantle once existed within that rising column of stone arrives at the surface wearing an entirely different face, carrying no memory in its crystal structure of the world it came from. Slow geology erases it. The ascent is the erasure. And so the question that haunted the people who knew this mineral intimately from the laboratory, who had measured its density and computed its sound speed and matched those numbers against the murmur of 10,000 earthquakes, was not whether it existed. They were certain it existed. The seismic record, the physics, the decades of high-pressure experiment, all of it pointed in one direction. Unmistakably, the question was how to hold it still long enough to call it by a name. How to preserve something that the planet itself would not preserve. How to get around the unhurried violence of geology, which had been dissolving the evidence for 4 billion years without pausing to consider that someone might one day want a sample. The answer, when it came, looked nothing like a solution. It looked like a wound. The Tenem meteorite, the L6 chondrite that fell in showers over Queensland in 1879, picked up from the dry Australian ground, catalogued and stored and traded through collections across the following century, carries inside it something that the slow interior of the earth never permits to survive. It carries shock veins. Dark, thin seams running through the rock like healed cracks, like the memory of a moment of extraordinary violence. Because before Tenem was a meteorite resting in a drawer somewhere, before it was a stone falling through the atmosphere above Queensland, before it was any of the things that happened to it on its long journey toward Earth, it was part of a larger body somewhere in the asteroid belt. And something hit that body. Something travelling at several kilometres per second struck it, and in the instant of that collision, the pressure inside those future veins climbed to roughly 23 to 25 gigapascals. The temperature reached approximately 2,000 degrees Celsius. For a few seconds, not minutes, not hours, seconds, conditions within those thin seams reproduced something very close to what exists naturally at the top of Earth's lower mantle, 660 kilometers below your feet. And then it stopped. The event ended. The heat dissipated almost immediately into the surrounding rock. The pressure dropped, and because the drop was so fast, because the quenching happened in an instant rather than over the geological timescales that allow bridgmanite to reorganize itself into something else, the mineral froze. It stayed. It did not have time to unmake itself, because time was precisely what it was not given. The shock created it, and the quench kept it, and the asteroid carried it. And the drift of the solar system eventually delivered it to Earth, and the atmosphere slowed it, and the ground caught it, and the dry Queensland air preserved it, and the people who found it in 1879 did not yet have the tools to understand what they were holding. The grains themselves are extraordinarily small, submicron to a few micrometers across, smaller than a red blood cell. Smaller than most of what your naked eye could resolve, even under reasonable magnification. You could not grip one. You could not pick one up in any meaningful sense. When the scientists who finally characterized bridgmanite in 2014 spoke of holding it, they meant something more intimate and less physical than the word suggests. They meant reading it. They meant directing a beam of synchrotron X-rays produced at the Advanced Photon Source at Argonne National Laboratory, X-rays fine and precise enough to interrogate a crystal structure smaller than a blood cell without destroying it, and reading back the diffraction pattern that the atoms inside the grain produced. The holding was in the data. The touch was made of light. Quick reminder, after years of lying awake with a racing mind, deep sleep finally became possible. Now learning comes easier, energy is real, and the mind stays sharp. Sleeping like a baby changed everything. If you want the exact system that made this possible, check the link in the pinned comments. And still there is the 40-year gap to consider, because it is one of the quieter ironies in the whole story, the kind that tends to go unremarked in the press release versions of this discovery. The compound was not unknown to science in 2014. Lin-gun Liu, working in the mid-1970s, had synthesized magnesium silicate in the perovskite structure inside a diamond-anvil cell, had squeezed the starting materials to the necessary pressure and watched the phase appear, had measured it and published it, had given the field the synthetic standard against which all subsequent work would be calibrated. That was 1974. 1975, humanity had been making Earth's most common mineral in the laboratory for roughly 4 decades before a natural piece existed in any collection anywhere in the world. And the reason it could not be named in all that time was not a failure of chemistry or physics. It was a rule. The International Mineralogical Association holds that a mineral is not a mineral until it has been found in nature. That is not a bureaucratic caprice. It is the consequence of a very old and reasonable distinction between things that occur in the world and things that human beings have manufactured to resemble them, and the distinction matters because a synthetic compound, however faithfully it reproduces the properties of some hypothetical natural substance, cannot carry the record that a natural crystal carries, cannot carry the impurities, the trace elements, the structural defects laid down by the particular conditions of a particular place at a particular moment in geological time. A natural holotype specimen is not merely a formality. It is evidence of a different and irreplaceable kind. And so, for the better part of 4 decades, the compound that Lin-gun Liu had made in the mid-1970s remained officially unnamed, officially unrecognized as a mineral in the full sense of the word, officially suspended in a curious limbo between existence and nomenclature. Science knew it. Physics had measured it. Chemistry had characterized it with increasing precision through every decade that followed. But the International Mineralogical Association could not name what had never been found, and the Earth, for reasons entirely its own, declined to yield a piece. And in that long silence between the laboratory synthesis and the naming, something remarkable happened. Something that belongs, perhaps, to the deepest and most patient tradition of how human beings learn to understand a world they cannot enter. They listened to it. Consider what the earth does. Constantly, without pause, beneath your feet and beneath the floors of the oceans and beneath the roots of every mountain range on every continent. It rings. Not loudly. Not in any register that the human ear can detect, but in the language of pressure waves, compression waves and shear waves that propagate outward in every direction from every earthquake, every volcanic detonation, every large landslide, every underground nuclear test, and every other event energetic enough to set the rock shaking, the Earth is always, in some sense, speaking. It has been speaking for as long as it has existed. And seismologists, over the course of the 20th century, learned to read that speech with extraordinary precision, learned to place their instruments at hundreds of stations scattered across the globe, and to triangulate the interior structure of the planet from the way those waves bent and slowed and accelerated and reflected as they passed through different kinds of rock at different depths. The technique is not entirely unlike the way a doctor uses sound to see inside a body. Press an ultrasound transducer against skin, and the machine sends a pulse of high-frequency sound into the tissue. Different tissues reflect that pulse differently, and the pattern of reflections builds an image of what the transducer cannot directly see. Seismology operates on a far grander scale and with waves produced not by a machine but by the planet's own violence, but the principle is the same. The rock that the wave passes through shapes the wave. The wave, read carefully, reveals the rock. What seismologists discovered over decades of such reading was that the Earth's interior was not smoothly uniform. There were layers, there were boundaries, sharp enough that waves passing through them changed speed abruptly, the way light bends when it passes from air into water, or from water into glass, and seismographs around the world, comparing the arrival times of waves from distant earthquakes, could feel those boundaries as clearly as a finger pressed against a windowpane can feel the difference between glass and frame. One of those boundaries sat at a depth of approximately 660 kilometers. At 660 kilometers, seismic waves sped up. Not gradually, sharply, in the way that only a sudden change in the physical properties of the rock could produce. And for many years, the precise reason for that speed change was a question that seismologists and mineral physicists circled together, each bringing half of the answer, neither fully able to complete it alone. The mineral physicists brought laboratory data. They brought the measurements made on synthetic silicate perovskite, on the compound that Lin-gun Liu and his successors had been manufacturing and refining in high-pressure cells for years. Measurements of its density under pressure. Measurements of how fast sound travelled through it. Measurements of its elastic properties at the temperatures and pressures that the lower mantle was calculated to maintain. And when they compared those measurements to the seismic velocity profile of the lower mantle, when they asked whether a rock made mostly of synthetic magnesium-iron silicate perovskite, compressed to the right pressure and heated to the right temperature, would transmit earthquake waves at the speeds that seismographs actually recorded, the answer was yes. The match was not perfect, as such matches rarely are in a science dealing with conditions that no experiment can fully reproduce. But it was close enough and consistent enough and reproducible enough that the inference hardened over time from possibility into something close to certainty. The lower mantle, the vast, hot, slowly churning layer that begins at 660 kilometers and extends all the way to the core mantle boundary, nearly 2,900 kilometers down, was dominated by silicate perovskite, by the compound they could make but not name, by what we now call bridgmanite. And the 660-kilometre boundary itself, the seismic discontinuity, was not merely the top of a layer, it was the site of a mineral transformation. Just above it, in the region called the transition zone, a mineral called ringwoodite was stable, a dense, high-pressure form of olivine. The same basic magnesium-iron silicate rearranged by pressure into a spinel crystal structure that packed the atoms more tightly together. As rock descended through the 660-kilometer line, the pressure and temperature changed in a way that made the spinel structure unstable, and ringwoodite, under those new conditions, broke apart. It did not simply melt, it reorganized. It transformed into two new phases, silicate perovskite and ferropericlase, that second mineral being a simple compound of magnesium, iron and oxygen, written as O, which shares the lower mantle with bridgmanite in the role of a quieter, less abundant partner. The seismic discontinuity that seismographs record at 660 kilometers is, in this understanding, the sound of a mineral reaction, the echo of ringwoodite becoming bridgmanite, millions of times over, wherever subducting rock descends past that depth. The boundary we hear is a transformation. The line in the earth is not a wall, but a threshold. This is what it means to read a world by sound. This is what it means to know something intimately before you have ever seen it. By the time Shauna and Chi Ma identified their natural grain in the Tenem meteorite and published in Science in November 2014, the scientific community already had, in a real and practical sense, a detailed portrait of bridgmanite. They knew its density. They knew its crystal structure, having determined it from synthetic samples. They knew how fast compressional waves and shear waves travelled through it. They knew where it lived and roughly how much of the lower mantle it composed, the figure settling through successive refinements of both the seismic data and the high-pressure laboratory measurements, around 70 to 80% of the lower mantle by volume, which is to say something like 38% of the entire planet. They knew it carried iron as well as magnesium in its structure, in a ratio that affected its density and its thermal conductivity and the way heat moved through it. They knew, in short, nearly everything that a mineral physicist would want to know about a substance, except the one thing that the International Mineralogical Association required before the name could be given: a piece of it in a drawer. There is something almost philosophical in that situation. A rock that makes up the majority of the planet, known in its properties, mapped in its distribution, understood in its behavior, and yet formally unnamed because no one had ever held a natural piece. The mineral existed in abundance beyond any other solid material on Earth. It had existed since the early eons of planetary formation, since the accreting mass of the young Earth first differentiated into core and mantle, and the pressures in the interior climbed high enough to force the magnesium-iron silicate into the perovskite structure. It had been there, churning slowly, for billions of years. And still it had no name of its own. It had a description, it had a formula, it had a structure, a space group, a measured elastic tensor. But it did not have a name. The naming, when it finally came, required not just the meteorite, but the right tool to read what the meteorite contained. And this is the detail that tends to be left out of the press release versions of the story. The detail that turns the 2014 discovery from a simple narrative of perseverance into something more genuinely interesting. A story about the tools of knowing, about how the question of what we can understand is always partly a question of what instruments we have at hand. In the years before 2014, attempts had been made to characterize the bridgmanite grains that might, in principle, be present in heavily shocked meteorites. The tool of choice for examining tiny mineral grains at that scale was the transmission electron microscope, a machine that works by passing a beam of electrons through an extremely thin sample and using the way the electrons scatter to reconstruct the arrangement of atoms within the crystal. It is a powerful instrument, capable of resolving structure at the atomic level, capable of seeing things that no optical microscope can approach. For many purposes, it is exactly the right tool. For bridgmanite, it turned out to be exactly the wrong one. The crystals, those tiny shock-frozen grains of silicate perovskite preserved in the dark seams of the meteorite, were extraordinarily sensitive to the electron beam. The beam carried enough energy to disorder the atomic structure of the grain before a meaningful measurement could be made. The crystal, bombarded by electrons, turned to glass. Not metaphorically. Literally, the ordered crystalline arrangement of silicon and magnesium and oxygen atoms that made the grain what it was, that made it bridgmanite rather than an amorphous mass of the same elements, was destroyed by the very instrument trying to observe it. The measurement erased its own subject. The grain became unreadable in the act of being read. This is a phenomenon with a name in materials science, amorphization under electron irradiation. It is not unique to bridgmanite. Several high-pressure mineral phases share this sensitivity. Because their crystal structures are metastable under the conditions of the laboratory and need only a modest energy input to collapse into a disordered state. But for bridgmanite specifically, the problem was acute enough that attempts to characterize natural grains in shocked meteorites during the 1990s and into the early 2000s kept running into it. You would find a candidate grain. You would prepare a thin section, you would center it under the beam, and the crystal would be gone before you could record its diffraction pattern. The door opened, and the room was always empty. What changed was not the mineral. What changed was the light. At the Advanced Photon Source, a particle accelerator at Argonne National Laboratory outside Chicago, electrons are driven around a storage ring roughly 1,100 meters in circumference at speeds close to the speed of light. As they travel around the ring, bending under the influence of powerful magnets, they emit X-rays. Not the broad spectrum, relatively gentle X-rays of a medical machine, but intense, brilliantly focused, highly coherent beams of precisely controlled wavelength. These are synchrotron X-rays, and they can be tuned and focused to a spot smaller than a human hair, smaller than a red blood cell, small enough to interrogate a crystal just a few micrometers across without disturbing the crystals on either side. The beam does not carry enough energy delivered in that way to amorphize the structure the way an electron beam does. It passes through the grain, scatters off the atomic planes within it, and produces a diffraction pattern, a record of the angles at which the X-rays deflect, which is as unique to a given crystal structure as a fingerprint is to a person. The machine at Argonne reads a grain smaller than a blood cell and returns, from the geometry of the scattered light, the full crystallographic identity of what it has just illuminated. It was this instrument and this technique, synchrotron micro-focus X-ray diffraction, that Oliver Chorner and Chi Ma and their colleagues brought to bear on the grains in the Tenom meteorite. The approach was not uniquely obvious. It required the convergence of a meteorite sample already known to be shock metamorphosed to the highest grades. A beamline at the Advanced Photon Source, fine enough to resolve features at the micrometer scale, and researchers who connected the technical capability of the instrument to the specific preservation problem that bridgmanite presented. The beam was gentle where the electron microscope had been destructive. The resulting diffraction pattern matched what synthetic silicate perovskite was known to produce, matched the distorted orthorhombic perovskite structure, the space group designation that had been determined from synthetic samples decades earlier. And with that match, with the X-ray data from a grain in a 95-million-year-old shock vein in a meteorite that had fallen to Earth in Queensland in 1879, the 40-year naming gap closed. The mineral finally had a piece in a drawer. And with a piece in a drawer, it finally had a name. Percy Williams Bridgman was born in Cambridge, Massachusetts in 1882 in a country that was only 17 years past the end of its civil war, in a century that had not yet imagined quantum mechanics or X-ray crystallography or the continental drift hypothesis. He died in Randolph, New Hampshire in 1961, the year the Soviet Union launched a man into orbit. Having lived long enough to see physics transformed several times over, and having been, himself, one of the forces that transformed it. His contribution was pressure. Not metaphorical pressure, not institutional or intellectual pressure, the literal physical pressure of matter compressed, of atoms pushed closer together than they would ever choose to be on their own. Held there by apparatus that Bridgman designed and built and improved across decades of meticulous work at Harvard. The problem Bridgman set himself was a simple one, in the sense that it could be stated simply, and a difficult one, in the sense that no one had come close to solving it when he began. To study matter at high pressure, at the pressures that might prevail deep inside the Earth, or inside a massive planet, or in the moments after an explosion, you need a chamber that will not rupture under that pressure, seals that will not leak, a way to apply force uniformly and controllably and measurably, and a way to make observations inside the chamber while it is compressed. Bridgman solved these problems one by one over a career that spanned nearly half a century. He designed a seal, the Bridgman seal, still used in modified forms, that became more effective the more pressure was applied to it, so that the vessel sealed itself against its own contents. He built high-pressure cells that could reach pressures far beyond what had been achieved before, and he used them to study the properties of hundreds of materials: water, mercury, ice, glasses, metals, polymers, biological substances, at pressures that had previously existed only in theory. He built in effect a new branch of experimental physics, one that operated in a regime the rest of the discipline had barely touched. For this work, for the invention and application of apparatus that generated pressures of tens of thousands of atmospheres and the discoveries made under those conditions, Percy Bridgman was awarded the Nobel Prize in Physics in 1946. By then his pressure cells had already inspired a generation of successors, and the trajectory was clear. The apparatus would grow more capable. The pressures would climb, and eventually the extreme interiors of planetary bodies, long accessible only to inference, would become, at least partially, reproducible in the laboratory. The diamond-anvil cell, the elegantly simple device in which two gem-quality diamonds with polished flat tips squeeze a tiny sample between them to pressures that reach and exceed those at the Earth's core, is the inheritor of Bridgman's tradition. The multi-anvil press, which uses a set of hard anvils converging from multiple directions to achieve very high pressures over a slightly larger volume, descends from the same lineage. Every experiment in which synthetic bridgmanite was made and measured, every determination of its density, its sound speed, its elastic moduli, all the properties that were later matched to the seismic profile of the lower mantle, was conducted in an instrument that traced its ancestry through decades of refinement to the machines that Percy Bridgman designed in Cambridge. The mineral named for him was, in a very real sense, made possible by him. not merely as a tribute, but as a fact of intellectual and technical history. There was some discussion in the period leading up to the naming about whether the most abundant mineral in the planet should be named for a person at all. The tradition in mineralogy of attaching individual names to discovered minerals is old and deep, a way of honoring those whose work made the discovery possible, and also a way of encoding in the permanent record of taxonomy, a thread of human narrative alongside the chemical formula. But the argument against person naming at this particular scale had a genuine weight. Here was a substance that composed roughly a third of the entire Earth, something closer in its universality to an element than to the specific local minerals that typically receive their discoverers' names. Something that vast, some argued, should carry a name reflecting that scale rather than reducing it to the biography of one scientist. The discussion was real, it was not merely academic. And the International Mineralogical Association's Commission on New Minerals reviewed the proposal and its reasoning and approved the name bridgmanite in June 2014. Several months before the formal publication appeared in Science in November of that year. The EMA reference number is 2014-017. The debate was resolved in favor of the name, and the argument for it was not simply sentimentality. Bridgman's pressure apparatus was the direct technological ancestor of every machine that had made or measured the mineral since Lin-gun Liu first synthesized it in the 1970s. To name the mineral for the man who built the tool that made it was not merely an honor. It was an accurate account of how the thing had come to be known. And there is something fitting in that. Something that has the quiet logic of a circle completing itself when you sit with it long enough. Bridgman spent decades pushing matter into states of extreme compression, into pressure regimes that existed outside his laboratory only at depths the planet guards most jealously. He could not reach those depths himself. No human being has, or likely ever will. But his apparatus gave the field a path into that hidden region, a way of touching, at least briefly and partially and in miniature, the conditions that prevail below 600 kilometers of rock. And in those conditions, in the diamond-anvil cells and multi-anvil presses that descended from his work, the mineral that makes most of the planet was first created and first measured. It was, in the deepest sense, his discovery before it was anyone else's, discovered not as a physical specimen, but as a set of properties mapped from outside the zone where the specimen lived. The naming honored that. The Commission recognized it. The long gap between synthesis and nomenclature was closed by a meteorite and an X-ray beam. But the name that filled the gap pointed backward, correctly and gratefully, to the man who had made the whole enterprise of high-pressure earth science possible. By the time the paper appeared in Science on the 28th of November 2014, the scientific community received it not as a complete surprise, but as the completion of something long anticipated. The natural specimen did not overturn what was known about the mineral. It confirmed it. The diffraction pattern from the tenom grain matched what synthetic silicate perovskite was expected to produce. The composition, the iron content, the ratio of magnesium to iron in the natural sample fell within the range that geophysicists had inferred from the density profile of the lower mantle. The natural piece told the story that the synthetic measurements had already suggested, and told it in the particular way that only a natural piece can, with the impurities and the structural nuances that no laboratory synthesis can quite replicate. the trace record of conditions that existed not in a pressure cell in a university building, but in the interior of a planetesimal that formed in the early solar system and was struck, violently, by something moving at several kilometers per second. The grain in the shock vein of the Tenem meteorite was not manufactured evidence. It was the real thing, pressed into existence by a collision that happened in space and preserved across more than a century of terrestrial storage, waiting in its rock for the instrument capable of reading it without destroying it. And with the name given, with the IMA approval in June and the science publication in November, the 40-year gap between making and naming officially closed. Bridgmanite entered the record. The most abundant mineral in the planet finally had a holotype, and the description block in the IMA's mineral register finally had a box that could be filled with something other than a synthetic compound's provenance. The thing existed, formally, completely, in the way that science requires things to exist before it will grant them permanent names. Outside, in all the ordinary world above that discovery, in the Queensland dust where the meteorite had fallen in 1879, in the Chicago suburbs where argon sits behind its security fences, in the offices and libraries of every geology department that received the paper that November, bridgmanite continued to exist exactly as it always had. Nothing changed in the lower mantle when the name was approved. The mineral went on circulating in the slow dark convection that it had maintained since the earth was young, pressing upward and folding back and pressing upward again in timescales that make human history invisible. The name was for us. The mineral did not need it. But the naming mattered, because names are how science organizes what it knows, and because the long gap without a name had been. In a subtle way, a gap in the organization of knowledge, a compound that everyone agreed was the dominant material of the planet's interior, discussed in hundreds of papers and reviews and textbooks, always with an asterisk, always with the workaround term silicate perovskite or SiO3 perovskite, never with the settled, permanent designation that allowed a single word to call up the whole structure of what was known. That word now existed, and the word was bridgmanite, and yet to understand why the word mattered as much as it did, it helps to go backward, not to the morning the paper appeared, but further, to the decades before any grain existed, when geophysicists were building their knowledge of the lower mantle not from specimens they could hold, but from something far more patient and far more indirect. From sound. Earthquakes, when they move through the earth, do not move through it uniformly. The waves they send outward travel at different speeds depending on the material they pass through, and seismographs, distributed across the surface of the planet, can read those speeds with extraordinary precision. They can tell you, from the way a wave bends and accelerates, that the material it passed through had a certain density, a certain stiffness, a certain resistance to compression. They cannot tell you the name of the mineral, they cannot hand you a grain. But they can describe the material so precisely that if you have measured that same material in a laboratory press under the right conditions, you can match the description and say, with considerable confidence, this is what the wave passed through. At approximately 660 kilometers beneath the surface, seismographs around the world have long recorded a sharp discontinuity, a place where the velocity of seismic waves jumps abruptly to a higher value. The Earth's interior, as read by those instruments, changes character at that depth in a way that cannot be explained by temperature or pressure gradients alone. Something happens to the material itself, and what happens, as laboratory experiments eventually made clear, is a mineral reaction. The mineral ringwoodite, which dominates the transition zone above that depth, breaks down under the increasing pressure and releases its component atoms into new arrangements. Magnesium and silicon and iron reorganize themselves into the distorted perovskite lattice that we now call bridgmanite, paired with the simpler compound ferropericlase, and the resulting materials are denser and differently elastic in precisely the way the seismic velocities require them to be. The 660-kilometer discontinuity, in other words, is not merely a line on a graph. It is the sound of a mineral reaction, propagated through the body of the planet and recorded by instruments on the surface. Every time an earthquake somewhere in the world sends waves downward through the transition zone, those waves cross the birthline of bridgmanite and return altered by it, carrying in their frequencies and arrival times the signature of a phase change that has been running continuously for billions of years. Scientists had been reading that signature long before they had a name for what produced it, and long before they had a grain of the actual substance in hand. This is one of the stranger facts in the whole story, and it bears staying with for a moment, because it upends the ordinary sequence in which we imagine knowledge proceeding. Usually we think of understanding as moving from the specimen outward. You hold the rock, you measure the rock, you describe the rock, and from that description you build a model of where the rock might be found and how much of it there might be. But with bridgmanite the sequence ran in reverse. The model came first. The seismic velocities described a material, and then laboratory physicists, squeezing synthetic silicate perovskite in diamond-anvil cells and multi-anvil presses, measured that synthetic compound's density and elastic properties at the relevant pressures and temperatures, and found that they matched the lower mantle's velocity profile with remarkable fidelity. The model of what was down there was built from earthquake waves and from the synthetic compound pressed into existence by machines, and it was built decades before a single natural grain confirmed it. Which raises, quietly, the question of why it took so long. If scientists had been synthesizing this compound since the mid-1970s and measuring its properties with increasing precision through the 1980s and 1990s, why did it take until 2014 to characterize a natural specimen? And the answer to that question is partly the answer to a narrower, more technical problem, one that involves what happens when you try to look at something very small and very fragile with the wrong instrument. Transmission electron microscopy had been, through much of the late 20th century, one of the primary tools for characterizing mineral grains too small to see by other means. It works by passing a beam of electrons through a thin section of material and reading how the electrons scatter, which tells you about the arrangement of atoms beneath the beam. For many minerals, it is extraordinarily powerful. But bridgmanite, as researchers attempting to characterize natural grains in the 1990s discovered, is exceptionally sensitive to electron bombardment. The beam does not merely read the crystal, it damages it. Under electron irradiation, bridgmanite's ordered atomic lattice breaks down, the grain amorphizes, its structure collapsing from an organized crystal into something closer to glass, and the information that the microscope was trying to read is destroyed in the act of reading it. The attempts to characterize these natural grains failed not because the grains weren't there, but because the instrument required to see them was also the instrument that erased them. It was a problem that had to wait for a different kind of light. Synchrotron X-ray sources, by the early years of the 21st century, had reached intensities and precisions that made it possible to focus a beam onto a single grain smaller than a red blood cell and read the diffraction pattern it produced, the way the X-rays scattered off the crystal planes, which, when analyzed, reveals the spacing of those planes, and through that the identity and structure of the mineral, without destroying the grain in the process. X-rays, unlike electrons, were gentle enough where electrons had been catastrophic. The Advanced Photon Source at Argonne National Laboratory outside Chicago is one of the most powerful synchrotron X-ray facilities in the country. Its beams are generated by electrons accelerated to very nearly the speed of light around a storage ring more than 1/3 of a mile in circumference, and the X-rays they produce are orders of magnitude more intense than anything available from a conventional laboratory source. It was there, in 2014, that the team led by Oliver Chauner brought their carefully prepared sections of the Tenom meteorite, positioned the microfocus beam onto grains that earlier instruments had either missed or destroyed, and read, at last, the diffraction pattern that confirmed what the seismic velocities had been suggesting for decades. The man whose name now attached to that confirmation had been dead for more than 50 years by then. Percy Williams Bridgman was born in Cambridge, Massachusetts in 1882 and spent his professional life at Harvard, where he built, over the course of decades, a series of increasingly ambitious pressure apparatus, devices designed to squeeze matter into conditions that did not naturally occur anywhere on the surface of the Earth, and to measure what happened to that matter when it was squeezed. His work was not glamorous in the conventional sense. He did not discover a new element or observe a distant galaxy. What he did, quietly and with extraordinary patience across a career that spanned the first half of the 20th century, was find ways to make matter obey pressures it had never encountered before, and then measure, with meticulous care, what it became under those conditions. He designed his own seals, his own pistons, his own measurement systems, because nothing existed that could do what he needed. He was, in the most literal sense, the first person to push matter systematically into the regime where Earth's interior lived, and to bring back reliable data from that regime. The Nobel Prize he received in 1946 in physics for the invention of apparatus to produce extremely high pressures and for the discoveries made therewith, was an acknowledgement not only of a body of results, but of an entire new domain of experimental science he had essentially created alone. He died in 1961, leaving that domain to others, and those others carried it forward into the diamond-anvil cell, the multi-anvil press, the synchrotron beamline, and all the instruments that followed. When Oliver Chauner and Chi Ma stood at the Advanced Photon Source in 2014 and read the diffraction pattern of a grain smaller than a red blood cell, they were standing at the far end of a chain of experimental ingenuity that Percy Bridgman had forged link by link. The name they gave the mineral was not chosen carelessly. It was chosen because, without the machines and the methods and the intellectual tradition that Bridgman's life represented, there would have been no way to make the mineral, no way to identify it, no way to understand what it was doing at the center of the planet, and no way to read it, finally, in a tiny frozen vein inside a stone from Queensland. The name is a kind of gratitude pressed into the periodic record of minerals, permanent and quiet. And yet the story of the deep earth does not end with bridgmanite. That would be too tidy, and the planet is not tidy. Bridgmanite occupies the lower mantle from roughly 660 kilometers down to roughly 2,890 kilometers, which is, as we have considered, a vast column of rock, by any measure, more than 2,000 kilometers of interior. The largest single layer in the planet, a place where pressure climbs from around 23 gigapascals at the top to somewhere above 125 gigapascals near the bottom, where temperatures rise from perhaps 1600 degrees Celsius to well over 2500 degrees Celsius, numbers that stretch and nearly exhaust the imagination. But beneath even that, beneath 2,800 kilometers of solid silicate rock, beneath the rain of the mineral we spent decades learning to know, there is something else. A thin and peculiar layer, a boundary zone, a place where even bridgmanite, that most durable and patient of minerals, transforms into something new. It is called the D double prime layer, written as D in geophysical notation, a designation that is less a name than an address, a symbol borrowed from a classification scheme that is decades old, and it refers to the lowermost portion of the mantle, the few hundred kilometers directly above the core mantle boundary at roughly 2,890 kilometers depth. Seismologists had known for a long time that this layer was strange. Seismic waves behaved oddly there, the velocities changed in ways that did not fit the smooth extrapolation of properties expected from the bridgmanite-dominated mantle above it. There was a seismic discontinuity at the top of the D layer that had resisted explanation for years. Something was happening there, something that altered the mineral assemblage and therefore the physical properties of the rock, and for a long time no one could say exactly what. The answer came in 2004. A team led by Murakami and colleagues working at extreme pressures in the laboratory discovered that at conditions corresponding to the base of the mantle, pressures above roughly 125 gigapascals, temperatures soaring past 2,000 degrees, bridgmanite itself undergoes a further structural transformation. The same magnesium-iron silicate that had been stable through the entire breadth of the lower mantle reorganizes its atoms one final time, shifting from the distorted perovskite arrangement that defines it into an even denser architecture. This new phase, which came to be called post-perovskite, had an arrangement of atoms that was better suited to the crushing conditions at the very base of the mantle. Independently, Oganov and Ono modelled and confirmed the same transition, and together these findings gave seismologists the explanation they had been looking for. The seismic anomaly at the top of the D layer was not a mystery of chemistry so much as a mineral boundary. Bridgmanite, at the floor of its own kingdom, transforms into post-perovskite, and the seismic velocities change because the rock's elastic properties change, and the D layer, that long puzzling region just above the molten iron core, is, in a meaningful sense, a belt of post-perovskite, a transformed version of the mineral that fills everything above it. Think of it this way. If you could somehow compress a spring until it clicked into a flatter, denser coil, not broken, not melted, but reorganized, the spring's behavior would change even though its material was the same. Post-perovskite is bridgmanite clicked into its ultimate form by the most extreme conditions in the solid earth. It is bridgmanite at the very end of what rock can do before it meets the liquid iron core below. This is what the planet looks like in cross-section, understood from a distance, inferred from waves and confirmed from crystals. A thin crust, a wide upper mantle, a transition zone at around 400 to 660 kilometers, threaded with the mineral ringwoodite and its neighbors. Then the long, bridgmanite-dominated lower mantle, the largest layer, the most abundant rock, the hidden heart of the world. And then, at the very bottom, that strange belt of post-perovskite wrapped around the core like a compressed final signature, visible only through its effect on the speed of seismic waves, and through the laboratory heroics of scientists pressing matter to conditions that exist nowhere on the accessible surface of the Earth. Bridgmanite has, in other words, both a ceiling and a floor. It begins where ringwoodite ends, at the 660-kilometre discontinuity, and it ends where post-perovskite takes over, near the core mantle boundary, at pressures that approach 135 gigapascals and temperatures that rival the surface of some distant stars. And the little Australian stone from Queensland, the Tenem meteorite that witnessed fall of 1879, is woven through more of this story than the bridgmanite alone. In 1969, more than 4 decades before Chawner and Chi Ma made their careful measurements at the synchrotron, another set of researchers named Binns and colleagues was examining sections of the same stone and found something preserved in its shock veins that had also never been seen in nature before. What they found was ringwoodite, the mineral of the transition zone, the phase that lives between roughly 500 and 660 kilometers depth, and whose breakdown at the 660-kilometre boundary produces bridgmanite in the first place. Ringwoodite had been predicted theoretically and synthesized in the laboratory, just as bridgmanite had, and just as bridgmanite could not survive the decompression of rising mantle rock. Ringwoodite also could not survive the journey from its natural home to the surface. It too unmakes itself. It too required a violent, fast event to trap it, a shock that reproduced high pressures and then quenched so rapidly that the mineral froze in place before it could revert. And it was there, in the Tenem meteorite, waiting, the same stone that would, 45 years later, yield the first natural specimen of bridgmanite, had already yielded the first natural specimen of the mineral that produces bridgmanite. Tenem is, in that sense, not merely a meteorite. It is a record of the deep Earth's phase transitions, a compact archive of the transformations that happen along the vertical column from the transition zone to the lower mantle. All of it frozen by a collision in space and delivered to Queensland in 1879 and lying in collections for decades while the science slowly caught up to what it contained. The pattern continued beyond the meteorite into a different kind of natural trap entirely. Diamonds form at great depth. Some of the diamonds that reach the surface began their existence not in the upper mantle, where most commercial diamonds crystallize, but at depths of several hundred kilometers, in the transition zone, or even in the lower mantle itself. These stones, called super-deep diamonds, are geologically rare and scientifically extraordinary, because when a diamond forms at depth, it can sometimes trap a tiny fragment of the surrounding rock, a mineral inclusion, sealed inside its crystal structure as if inside a vault. The diamond then carries that inclusion to the surface, protected from decompression by its own rigid lattice. The diamond does not transform, the diamond does not unmake itself, and so the inclusion inside it arrives at the surface, still bearing the crystal structure it had at depth, still bearing the composition it had at depth. A messenger from a world that cannot otherwise send messages. It was through exactly this mechanism that the third major mineral of the lower mantle finally received its name. Alongside bridgmanite, which makes up the bulk of the lower mantle, and ferropericlase, the magnesium-iron oxide that accounts for much of the rest, there is a third significant phase, calcium silicate perovskite, Cassio3 in the perovskite structure, the same ABX3 framework, but with calcium and silicon in place of magnesium and silicon. This phase, like bridgmanite, is predicted to be abundant in the lower mantle. Like bridgmanite, it cannot survive decompression, and could not be named under the International Mineralogical Association's rules. For the same reason, no natural holotype specimen existed. And then, in 2021, Schorner and colleagues published another paper describing an inclusion in a diamond from the Botswana area that carried exactly this phase, preserved at last in a natural trap. They named it diamond-anvil, after Ho Kwang Mao, the high-pressure physicist whose decades of work at the Carnegie Institution had done so much to advance the understanding of deep earth mineralogy. Diamond-anvil, a name, finally, for the third pillar of the lower mantle. The same logic that had finally allowed bridgmanite to be named, a fast trap, a preserved grain, a beam of X-rays gentle enough to read it, applied again, this time through a different natural vault, the rigid embrace of a diamond rather than the frozen shock veins of a meteorite. And in between these two namings, in the same year that bridgmanite was first identified and named from the Tenem stone, another team announced another finding from a super-deep diamond that changed how scientists understood the region just above bridgmanite's ceiling. Pearson and colleagues in 2014 described a tiny inclusion in a diamond from Brazil. An inclusion that carried not only ringwoodite, but hydrous ringwoodite that contained water molecules locked into its crystal structure, not as liquid, not as ice, but as hydroxyl groups chemically bound within the mineral lattice itself. This mattered enormously. Ringwoodite, the mineral of the transition zone, has a crystal structure that is, in principle, capable of accommodating water in this way, and for years the theoretical question had been how much water the transition zone might hold. The Pearson diamond answered it, at least in part. It showed that at least some ringwoodite in the transition zone carried measurable water, which implied that the transition zone as a whole might hold more water than had previously been thought, perhaps. Some estimates suggested an amount comparable to the water in the world's oceans, locked invisibly in the rock rather than sitting on the surface in blue pools and currents. The ground beneath us holds water we cannot see, in minerals we cannot hold, at depths we cannot visit, and the knowledge of it came from a grain smaller than a hair's breadth, sealed in a diamond, carried to the surface by processes we are still working to fully understand. What runs through all of this, the Tenem meteorite, the super-deep diamonds, the synchrotron beamlines and the diamond-anvil cells and the multi-anvil presses, is the same fundamental situation. The deep earth keeps its most important materials locked away. The planet is not secretive by intention. It simply operates at conditions so far removed from the surface that its minerals cannot survive the journey upward. They transform, they decompress, they revert to lower pressure forms that look, to the eye examining a volcanic rock or a mantle xenolith, like nothing more exotic than the ordinary minerals of the upper layers. The deep earth speaks only through indirect channels, through the speed of seismic waves, through the density profiles inferred from those waves, through the laboratory experiments that reproduce deep conditions in miniature, and through the rare and accidental traps, the frozen shock veins and the diamond vaults, that occasionally carry a small grain of the real thing to a place where it can be. Read. Bridgmanite matters, then, not only as a mineralogical curiosity, not only as the most abundant solid mineral in the planet, but as the substance whose properties govern the behavior of the largest layer of the Earth. Consider what that means in practical terms. The lower mantle, that 2,000-kilometre column of bridgmanite, dominated rock from 660 to 2,890 kilometres depth, is not static. It is not simply a solid rind of rock sitting inert around the core. it convects. Very slowly, over geological timescales, the material in the lower mantle moves. Hot rock near the core mantle boundary is slightly less dense than the cooler rock above it, and over millions of years it rises, while cooler material from above sinks down to take its place. This convective overturn, this imperceptibly slow churning of the largest layer in the planet, is driven ultimately by heat from the core and from the decay of radioactive elements. And it is the deepest engine of the geological activity we observe at the surface. The rate at which this convection occurs, the patterns it takes, the way it transfers heat from the core to the upper mantle and eventually to the surface, all of this depends on the physical properties of the rock that makes up the lower mantle. And the rock that makes up the lower mantle is, above all else, bridgmanite, its viscosity, the resistance with which it flows, which determines how fast or slow the convective cells cycle, is a property of bridgmanite. The way heat moves through the lower mantle is partly governed by how heat-conducting bridgmanite is. The way seismic waves travel through the deep earth, which is how we map the mantle's internal structure and infer its temperature and composition, depends on bridgmanite's elastic properties. Even the electrical conductivity of the lower mantle, which influences how the Earth's magnetic field interacts with the deep interior, is affected by bridgmanite's iron content, specifically by the ferrous and ferric iron that the natural mineral carries and that a pure synthetic sample made in a laboratory cannot fully replicate. This is one of the reasons, beyond the naming formality, that the natural specimen was scientifically valuable. The holotype grain from Tenom carried actual iron in actual proportions, iron that had equilibrated at actual deep earth conditions. And analyzing that iron told scientists things about the natural mineral's behavior that the synthetic compound, however well characterized, could not. The mantle convection that bridgmanite's properties regulate is also, ultimately, the engine behind plate tectonics. The movement of tectonic plates at the surface, the slow drift of continents, the opening and closing of ocean basins, the building of mountain ranges, and the generation of earthquakes and volcanoes is driven by the convective overturn of the mantle, which pulls plates along at the surface and pushes them back down at subduction zones. The deepest driver of that convection is the lower mantle. Bridgmanite, a mineral we could not see, could not name, could not hold, until a grain of it arrived frozen in a shock vein inside a stone that fell on Queensland in 1879 and waited, patiently, for 135 years, while the science developed the tools to read it. The perovskite architecture that bridgmanite adopts, that ABX3 framework, the same arrangement of atoms first described in the mineral calcium titanate, turns out to be one of the most versatile structural templates in all of materials science. The same geometry that bridgmanite uses to organize its magnesium, iron, silicon, and oxygen atoms, holding stable at extreme pressures in the deep mantle, is also used in entirely different chemical compositions by some of the most technologically significant materials of the present. Perovskite solar cells, which have generated considerable scientific attention in recent years, exploit the same crystal framework, not with silicon and magnesium, but with lead, iodine, and organic molecules, to absorb sunlight and convert it to electricity with an efficiency that has improved remarkably quickly since the architecture was first applied to photovoltaics. Certain superconductors, materials that conduct electricity without resistance at low temperatures, also crystallize in perovskite or perovskite-related structures. The geometry is not the same as the chemistry. But the underlying architectural principle, the way the atoms pack and relate to one another in this particular framework, appears, across wildly different compositions and conditions, to confer properties that are useful in ways that range from the most fundamental geophysical processes to the most practical technological applications. The mineral that governs the deep earth and the material being explored for next-generation solar panels share, at the level of atomic geometry, the same essential blueprint. There is something quietly remarkable in that connection, an unexpected thread between the interior of a planet and the surface of a solar cell. A reminder that nature uses a limited vocabulary of structural arrangements and applies them, with variation, across an enormous range of contexts. What we have been following, through all of this, is a single and very old question: what is most of the Earth actually made of, and how did we come to know it? For most of human history, the answer was simply unavailable. We could dig, and we could mine, and we could examine everything that volcanoes brought to the surface, and we could catalogue the minerals of the crust with extraordinary thoroughness. But the crust is thin. The crust is the skin. Everything beneath the crust, the mantle, the core, the vast interior of the planet, was sealed away from direct inspection, accessible only by inference, only by the slow elaboration of indirect methods. And the deepest part of the mantle, the lower mantle, was the most sealed of all, because its minerals transformed on the way up, because decompression erased the evidence, because the very rocks that dominate the Earth's interior cannot survive the journey to where we might see them. What replaced direct inspection was a combination of listening and squeezing. Listening to earthquakes, using the global network of seismographs that records every significant motion of the ground anywhere on Earth and tracks how seismic waves travel through the planet's interior, bending and reflecting off boundaries and slowing or accelerating as they pass through materials of different density and elasticity. And squeezing, using the machines that Percy Bridgman first designed, then refined by generations of high-pressure physicists, to reproduce, in a tiny volume of laboratory space, the conditions that prevail hundreds of kilometers down. Squeeze the right minerals at the right pressures and temperatures, measure their densities and elastic properties, compare those measurements to the seismic velocity profiles derived from earthquake data, and see if they match. If they match, you have identified, by inference and analogy and careful reasoning across two independent lines of evidence, what the deep earth is made of. You have read a fingerprint on the far side of a locked door. That is how bridgmanite was known for decades before a grain of it existed in a laboratory as a natural specimen. Seismologists detected the 660-kilometer discontinuity, that sharp jump in seismic wave speed recorded by instruments around the world, and recognized it as a phase boundary, a place where mineral structure changed abruptly and matched it, through laboratory experiments, to the breakdown of ringwoodite into bridgmanite and ferropericlase. Geophysicists measured the seismic velocity profile of the lower mantle as a whole and matched it, layer by layer, to the density and elastic properties of synthetic magnesium-iron silicate perovskite, squeezed at the relevant pressures and temperatures. They knew the mineral's sound speed before they knew its name. They knew its density before they had held a grain of it. They mapped the rock that makes up most of the Earth using earthquake waves as their instrument and high-pressure physics as their decoder ring, and what they found, before Schorner and Chimar ever positioned their synchrotron beam over the Tenom shock vein, was a detailed portrait of a mineral they had never seen. The 2014 discovery did not overturn that portrait. It confirmed it, which is its own kind of scientific satisfaction. Not the excitement of finding something entirely unexpected, but the deeper quiet of finding that the inference was right. That the waves and the squeezing and the decades of careful modelling had been pointing at a real thing. That the locked door had been locking in exactly what the fingerprints suggested. The natural grain, submicron and fragile and frozen in the dark seam of a stone from Queensland, matched what the models had predicted. The perovskite structure. The magnesium and iron and silicon and oxygen in the right proportions. The confirmation that this was what the lower mantle was made of, not as a theoretical construct or a laboratory compound, but as a mineral that existed in nature, that had a natural occurrence, that could be named. It could be named. After 40 years of knowing it and not naming it, after the long constraint of the International Mineralogical Association's rule that a natural holotype specimen was required before a name could be assigned, the grain from Tenom provided the holotype. And in June of 2014, the IMA approved the name bridgmanite in honour of Percy Williams Bridgman, whose Nobel Prize in Physics, received in 1946, rested on the very apparatus tradition that had made the synthetic compound possible in the first place, and whose intellectual legacy ran through every diamond-anvil cell and multi-anvil press in every high-pressure laboratory in the world. The paper was published in Science on the 28th of November 2014. The naming vacuum that had persisted since Lin-gun Liu synthesized the phase in the mid-1970s was closed. The ground beneath your feet right now is largely bridgmanite, not the ground immediately below, not the soil or the bedrock or the upper crust. But if you could extend a line from wherever you are standing downward through all the layers, through the crust, through the upper mantle, through the transition zone and all its ringwoodite, and into the lower mantle, which begins around 660 kilometers down and runs for more than 2,000 kilometers after that. The dominant material of most of that column would be bridgmanite, the mineral that fills roughly 55% of the Earth's volume by depth, the mineral that constitutes around 70 to 80% of the lower mantle, the mineral whose viscosity and thermal properties and ion partitioning govern the slow convective engine that drives the tectonic plates whose motion shapes the continents and the seafloors and the mountain ranges above. Most of what the planet is made of, most of what it has ever been made of, since the early Earth differentiated into its layers billions of years ago. And until a decade ago, no human eye had ever seen it. That is not a failure of science. It is, in its way, a testament to how science actually works, not always through direct observation, not always through specimens in hand and minerals in a drawer, but sometimes through inference and analogy and the careful alignment of two independent lines of evidence until they point, converging, at something real. The seismologists who read the 660-kilometer boundary from earthquake data, the high-pressure physicists who measured the elastic properties of synthetic silicate perovskite in their diamond-anvil cells, the geophysicists who matched the mantle's seismic velocity profile to the modelled properties of that compound, they were doing science without a specimen. They were knowing a mineral without seeing it. The knowledge was real. The picture they assembled was accurate. The grain in the Tenom shock vein simply confirmed, with the authority of natural existence, what had been understood by other means for a long time. But there is something the grain provided that the inference could not. A reality. A thing that had been there, in the dark, under pressure, a real crystal grown by real geology in the deep interior of a real planet, waiting in a small dark seam of a stone that travelled through space for billions of years and fell on Queensland in a summer shower of rocks in 1879 and lay in collections for decades and was finally read by a beam of X-rays in a facility outside Chicago in 2014. The grain did not change what was known. It changed what was held. It made the abstract intimate. It made the inference into matter. That is a distinction that matters in a way that is hard to fully articulate, but that sits somewhere near the center of why science is a human activity and not merely a computational one. Knowing is not the same as holding. Understanding is not the same as touching. The models were right, and the grain confirmed the models, but the grain also made bridgmanite real in a way the models could not, gave it provenance, gave it a natural occurrence, gave it the status of a mineral rather than a compound, gave it a name. The difference between a mineral and a compound synthesized to replicate a mineral is in the formal rules of mineralogy. The difference between something that exists in the world and something that has been made to exist in a laboratory. A small distinction in some ways, a necessary one in others. The Tenem meteorite, that quiet traveller, that stone from a parent body shattered by a collision at several kilometres per second somewhere in the asteroid belt, that witnessed fall of 1879. Has now yielded two of the most important natural mineral specimens in the history of deep earth science. Ringwoodite, found there first in 1969 by Binns and colleagues, the mineral of the transition zone, the phase whose breakdown at 660 kilometres creates bridgmanite. And bridgmanite itself, found there in 2014 by Chona and Chi Ma and their collaborators. The mineral of the lower mantle, the commonest rock in the planet, both of them locked in shock veins, both of them preserved by violence, both of them invisible to slower geologies. It is a small stone, a few fragments in museum collections, unremarkable to look at, dark and dense, crossed with those thin black seams of once molten rock that are the frozen records of a cosmic collision. You would not pick it up off the ground and know what it was. But inside it, if you knew where to look and had the right tools and the right beam of light, you would find a cross-section of the interior of the Earth, the two minerals that dominate the transition zone and the lower mantle, preserved by the only kind of event fast enough to trap them. The planet we live on is mostly a mineral we could not name and could not hold until an accident of violence in deep space and a fall of stones over a patch of Australian sky more than a century ago conspired to deliver a sample to the people who would eventually have the tools to read it. And the reading, when it finally came, confirmed what the listening had already told us. The ground beneath us is mostly a mystery made familiar. The rock we know best by its absence. Wherever you are tonight, in whatever room, in whatever country, listening to this as the day settles into the dark, you are resting on the thinnest of skins over a world of bridgmanite. The lower mantle begins roughly 660 kilometres below your bed, and it runs for more than 2,000 kilometres after that, and it is churning, as it has always churned, carrying heat upward from the iron core at the centre, driving the slow movements that raise mountains and open seas, doing all of this in complete silence, in complete darkness, at pressures that would reduce any instrument we have ever built to rubble, in a language we learnt to read, not by going there, but by listening, very carefully, to the way the ground shook when the earth moved, and matching that sound to the behaviour of tiny compressed samples in the quiet laboratories where people spend their lives learning to speak the language of the deep. If this kind of slow journey into the dark interior of things is useful to you as you find your way to sleep, there are more stories here of the same unhurried kind, more descents into the hidden layers of the world, more careful accounts of the things we know and do not yet know and came to know by unexpected means. They will be here whenever you want them. And if you feel inclined to leave a word in the comments about where in the world you are listening from tonight, I would genuinely like to know. The comments are there, and I read them. And there is something quietly pleasing about knowing that people in many different places are lying in the dark listening to the same story about the rock that makes up most of the planet beneath all of them. You have followed this a long way. From a paradox, a mineral everywhere and yet unseen, down through the seismic boundaries, through the shock veins, through the beam of X-rays in a facility outside Chicago, through the man whose pressure machines made it possible, to the floor of the mantle where even bridgmanite transforms one final time and becomes something denser still, and on to the small stone from Queensland that had been holding two of the deep Earth's most important minerals inside it for longer than any human institution has existed. That is enough for one night. You do not need to hold it all. Some of it will be there in the morning, and some of it will have dissolved into the hours between now and waking, which is as it should be. The lower mantle will still be churning. The bridgmanite will still be there. The Tenem meteorite will still be waiting in its cabinet, crossed with its dark seams, patient as it has always been. History will still be here in the morning. For now, rest.